All right, so welcome to lecture 18. Today we're going to talk about classification of combinatorial surfaces. This is sort of our second part of this attempt to prove the main theorem in algebraic topology. So let me remind you what the setup is. We're starting with a combinatorial surface. And that means a finite set of polygons with edges directed labeled by letters, with each letter appearing twice. And what we want to do is we want to start from an arbitrary combinatorial surface, and we want to modify it using certain simple key operations. And the operations that we're going to be using, there's really only two of them. One of them is to reduce a pair of edges, A. So when we have a situation like this, let's call the other things B, C, D, it doesn't matter what the other ones are, then these two pair of A's have opposite directions, and we can go from this, essentially by identifying or gluing together those two edges, we can go from that to B, C, D, and the edge A is now inside and folded over. So that's one thing that we can do. In terms of words, if we have a word, let's say we read like this, A inverse, D, C, B, then we can replace that just by collapsing the A and the A inverse to D, C, B. That's our first operation. And the second operation is cutting and pasting, essentially. So we have some polygon, A, B, C, D, E, F, let's say. And then we are allowed to make a cut anywhere we like, let's say here. And we'll introduce a new edge, G. And, well, then we have to look for where the other edge A or F is. Let's say we happen to have another piece over here with an A part there and maybe some other stuff there, G, H, doesn't matter. Then the idea is that we can cut off a piece of this polygon, say that piece there, and we can glue it back on to another polygon, or in fact the same polygon. So what would happen here is that we would move this piece over here. Let's say, I shouldn't put G, I should put, say, H. We could glue this piece here onto the other A section right there. And to do that, we might have to flip it if necessary. So the piece would go over here. And see, there'd be an A in this direction, and then followed by a G, and then followed by an F. So what would happen is that this piece here would be cut off and moved over there. Okay, and what we want to do, our aim, is to get our given combinatorial surface in one of our three standard forms. Either just a sphere, so it looks like A inverse, or a bunch of essentially cross caps. This first one's a sphere. Here we have maybe K cross caps. This will be, depending on how many pairs we have, or a bunch of handles, things with the form A, B, A inverse, B inverse, C, D, C inverse, D inverse, up to possibly E, F, E inverse, F inverse. So say N handles. All right, so that's our aim, to start with a general combinatorial surface, to make operations of these two simple kinds, and to convince ourselves that we can get into one of these three standard forms. All right, so let's begin. So we're going to do this in a number of steps, and our first step is to take our connected combinatorial surface. I suppose I should have mentioned that we're assuming that thing is connected in the sense that we can put all the polygonal pieces together, and what we do is we take our surface and glue or match the polygons together one at a time, to form one single planar polygon. So, for example, we start with one of the pieces, and it's labeled A, B, G, H, whatever. And then we choose any one of these free edges, say A, and, well, maybe it's best to look at it this way. Each of these edges A, that the edge A there might be repeated somewhere here, okay? So there's at most two A's that appear in the whole thing. But if that A only appears once here, it means that it must appear on some other piece. Okay? So we look around here for an edge which only appears once along here. Let's say A, and that means that there's another piece somewhere else that has an A piece, and then we move that piece and glue it on there. Okay? Now we have a slightly bigger piece with some more edges, C and D, and we keep doing that. We keep looking around here for a free edge, in other words, an edge that only appears once, and we look out on our selection of pieces, and we find another one, say B, and then we move this B there, match it up, so now we have a bigger and bigger polygon in the plane. At no point are we matching up edges here with edges on the same polygon. We're not wrapping this polygon around. This is staying planar. Okay, and our assumption is that we can keep doing this and we exhaust all the pieces. That's what we mean for it to be connected. So at the end of this step one, we have a single polygon with lots of edges, each edge appearing twice. So we end with something that looks like, okay, I'll draw as an example an octagon. We have something like this with edges that appear, all the edges are appearing exactly twice. Two A's, two B's, and so on. So our entire combinatorial surface is represented by one polygon or one word. So now one word describes our surface. Okay, now second step. Step two. is we've got to cut and paste so that we only have one vertex. Okay. So what we want to do is we want to modify so only one vertex, maybe we should say vertex type, occurs. All right, so what does this modification involve? Well, it involves, first of all, collapsing. So first, whenever possible, collapse an AA inverse pair. Okay. So if at some point we have, say, a C and a C inverse, like this, then at this stage we'll recognize there's two adjacent C here's with opposite directions. We're going to collapse them according to operation 1. That's the sensible thing to do, so we get rid of the obvious simplifications. Then what we're going to do is we're going to have a look at all the vertices. And so then what we do is we divide our vertices into equivalence classes. Via the identification of edges. Of our polygon. And let's do an example. So as an example, I'm going to have a look at that same example that we talked about last time. So A, B, C, D is a square. G, D, E is a triangle. Here's a two-gon with sides A and G, and a pentagon C, E, B, F, and F. That's the example that we talked about in the last lecture. So let me use that to illustrate what we're going to do here. So our first step is to glue all these things together. Let's do that first. So our step 1 on this would be to glue all these things together to form a planar polygon. So let's start with, say, this one here. A, B, C, D. And we attach some things. Say along that edge A there, we're going to attach this one here. And how does that work? Well, we have to move it around so this A edge lines up with that one, and then the G edge is going to come down like that. And then we could stick this triangle on via the D edge. So we just move it around so the D's line up, and then the G edge will be here, and the E edge will be there. And finally, we could take our pentagon and match it up, say, on that C edge. But to do that, we'd have to flip it over, because that C is going up. We want to flip it over. That's fine. So we go C, and then E, and then B, and then F, and then F. All right. So now we've got one polygonal piece that captures everything. And let's clean it up a little bit. There's 1, 2, 3, 4, 5, 6, 7, 8 sides. So we can rewrite that as an octagon. And I'll just record what all the edges are. There's a B, and then an F in this direction, an F, a B, an E, a G, and a G. All right, so we've completed step 1. All right, now how does step 2 go? Well, the thing we said is that first, whenever possible, we're going to collapse adjacent pairs. Are there any such opposite directed pairs? Yes, here G and G are appearing with opposite things, so we can collapse the G's. So let's do that. So we went from here to here. So if we collapse the G's, then we're going to have just a hexagon. There'll be 6 sides. And let's say starting with B, and then F, and then F, and then B, E, and E. Okay, so now let me use this to illustrate what I mean over here. I want to divide the vertices into equivalence classes. I want to say which vertices here are really the same. All right, so let's choose one vertex. Let's say that one there, and call it let me call it A. All right, so this A is at the bottom of E and the bottom of B. The bottom of E is right there, so that's got to also be the vertex A, and the bottom of B is right here. That's also got to be the vertex A. And if we go, say, over here, from the bottom of E to the bottom of B, then we're going the bottom of B to the top of E, and that's over here, and then we're going to go to the bottom of E, which is over here, and so we're back to where we started. So that's a closed loop. So there's also a second vertex. Let's call this one B. And this is at the top of B and the top of F. So that's also at the top of F, and that's also the top of B, yes. And just to check, if we go around this way, from the top of B to the top of F, and now we're at the top of F. Now we get to the bottom of F, which is over here, and then we go to the top of B, and now we're back to where we started. Okay. So in this case here, we've divided the corners of the polytope into essentially 2 vertices. So these 3 corners are one equivalence class, and these 3 corners are another equivalence class. And what we want to do is we want to only have one equivalence class. That's the main step now. Okay, so if there are 2 or more classes of these vertices, we consider a particular class. Let's say, okay, B1 up to BK with at least 2 elements. And we reduce the number of elements in this class by 1. How do we do that? So here's the general kind of picture. So suppose we have there's some BI, and okay, then the polygon can do something when it wants, and then eventually over here there's another, say, BJ, and then it does whatever it wants. And let's say these vertices, and that might be a P and that might be an R. Okay. So this edge, whatever it is going to be repeated somewhere. It's not going to be repeated here, because if it was repeated here, then this would be a vertex with only 1 in this type. So this edge, whatever it is, let's call it A, must be found somewhere else. Let's say here. It would have to be pointing this way. Okay. What we're going to do is we're going to cut and paste. So we're going to take this occurrence and we're going to cut there. Okay. So we're going to cut, forming a new edge, and we're going to take this piece here, and we're going to take it and move it and adjoin it right there. Okay, so what happens there? Well, the BJ, and this has got to be R, the BJ is there. Let's call this B, let's say. So there will be a B here. This will be the vertex P. So after we've done this, what's happened is that this part of the polygon has been removed, and this part has been added. Now what has happened to the vertices? Well, this is still the vertex of type P. This is still the vertex of type R. But this occurrence of B has now been glued to this occurrence of B. We've essentially replaced an occurrence of B with another occurrence of P. So the number of B's has gone down by this procedure. That's our basic strategy. And let's just have a look at what it would look like for our example there. So in this example, if I have a look at here, let's decide to eliminate the B's. Okay? So I'm going to choose one of the B's. It doesn't really matter which one. Let's lop off this top one here. Okay? So I'm going to lop off that triangle. And I have to look for one of the places that I can attach it to. Well, let me attach it right here. There's an F edge here, and there's an F edge here. So I'm going to attach this triangle right here. Okay, so let me label the edges correctly. So here was F. This is coming over here. I had to flip it over. This is now the B edge. And this new edge, I should give it a name. Let's call it, well, we've only got E's, B's, and F's, so let me call that A. I'll orient it in that direction. And then over here, there will be an edge A like that. So what I'm getting is, well, I still get another hexagon. The number of sides hasn't changed, but now it looks like an A followed by a B in this direction, followed by an A in this direction, and then a B in this direction, an E, and an E. Now what about the types of the vertices? Well, these three are still type A, as they were before. But this new one that I've added is really the same as this one. So I'm going to hit here. So this is also type A. And the other two are going to be of type B. Let's just check that. Okay. So let's just have a look around here as we go around here from the top of A to the top of B. Then we're at the top of B to the top of A. We're back to where we started. So that is a closed loop now. And you can check that the loop involving A now involves this one. Okay, well, since we're doing well, let's do it one more time. We want to continue this process to get rid of all the B's. So let's do it again. Let's cut off this one here. So we're going to cut off this triangle now with a new edge, which we might call C. And we'll take this triangle and move it out, and we'll attach it perhaps right here along the A edge, which matches up with this A edge. Okay, what are the other edges over here? A in this direction, then B in this direction, and C in this direction. And so that gives us, well, it's another hexagon. E, E, B, B coming in this way, C, and C. Okay, and now what's the edge, the vertex situation? These are all edges A, and this was also a vertex A before. And this new one here is also an A. It's between the B and the C, so that's an A. And so we see now that there's only one more vertex B. But if there's only one more vertex, it means that we're in a situation where we can collapse some edges. Because if there's only one vertex, it means that when we go from here to here, we're back to where we started. That means that we know we can collapse those two edges. All right, so let's do that. So let's collapse those edges. So we're going to collapse those edges. And now we'll only have 4 edges. So I'll draw it as a square. And now we have C, C. Those B's are eliminated, and E, and E. And now all the vertices are now of type A. If you walk around, you'll see you have to go past all 4. All right, so that's our second step. So our second step is to cut and paste so that we are guaranteed that all the vertices are of the same type. Okay, so we'll assume that we've done that now. All right, so our third step is to obtain a normal form or standard form for same direction edges. So normal form for same direction edges. What do I mean by same direction edges? Well, it just means that when we read through them, they're pointing in the same direction. So this C and this C, they're in the same direction. So we call these C a same direction edge. In fact, E are also same direction edges here. But in general, some of the edges will be sort of opposite each other, like A inverse, and the other ones will be same direction, like A. So let's just concentrate on same direction edges. So we assume we have an edge, and then we have some other ones. Okay, we don't really care what it is. And then we have another edge, A, and then some more stuff. Very general. So what are we going to do is we are going to cut from the top of one A to the top of the other. We're going to cut that piece off. So now we have 2 pieces. And let's say that the new edge that we're creating is called C. And then we're going to take this piece, let's call it this one here, that we're going to move, and we're going to move it so that it's adjacent to the A edge. We're going to glue it, this A edge, to this A edge. Okay? So just imagine taking this piece, and now we're going to move it. Well, we have to move it over here, but we also have to turn it over. Okay? So it'll be, I'll just put it over here momentarily. So there's A. And then there will be well, after the A comes a C in this direction. And then there's lots of other stuff. Okay. So I've moved this edge, this whole piece over there, after I've made the cut from the top of A to the top of A. And after we've done that, what's happened? Well, if we're looking sort of at the boundaries we're going around here, there's now a C edge, namely this one here, and followed by another C edge. And then there's other stuff. So the effect is that we've replaced 2 separate A edges, which are in the same direction, with 2 connected C edges in the same direction. This is the kind of thing we want, right? We want pairs A, B, B, C, C. So that's what we've done. We've replaced these random pair of same direction edges with an adjacent pair. And we haven't affected any of the other ones. The other ones that were adjacent are still adjacent. And we haven't changed the one vertex nature of the process. There's still only one vertex around. And now we also observe that once edges are together like this, in other words, sort of like a CC pair, then further cuts and pastes will not affect them. Further cuts and pastes will not separate them. All right, so now we can, of course, continue this. We've got the A's, which were separate before, had now been replaced by the C's. If now there are another pair of same direction edges which are separated, we can do the same trick and replace them with another pair of same directed edges which are together. So we can continue this till all the same direction edges are together in pairs. Of course, the opposite direction edges might still be around them. Still might be lots of them. And that's what we have to deal with now in the next step. By the way, we don't need to do anything more in this example. It's already in the situation we like. There's a pair of C's and a pair of E's. This is C, C, E, C, C, E inverse in our notation, and that's already in our standard form. All right, so step 4 is normal form for opposite direction edges. Okay, so the situation here is that we have one pair of edges, let's call them A, and they're in the opposite direction, so it's something like this. They're separated by pieces of the polygon. But they're in opposite directions. As we go around, one is going this way and one is going the other way. Okay, so in particular, this could be, if there weren't any other edges, this could be a sphere. That's a special case. That's sort of our one of our standard forms. So let's suppose that it's not a sphere. We can exclude that. And so we assume these A's are not adjacent. Because if they were adjacent, then we could collapse them. And then they'd be gone. Assume A's are not adjacent, otherwise collapse them. So let's have a look at the sort of the top and the bottom separating the A's. So there must be a common edge. In the top and the bottom. Okay, what do I mean by top and bottom? In the picture, so this is the top, separating two parts of the AA pair, and this is the bottom. And I claim that there must be some edge, say B, which occurs in the top, and it also occurs somewhere in the bottom. Well, otherwise, there must be a common edge in the top and bottom. Otherwise, well, think about think about what this vertex is. This vertex is going to be associated to this vertex. Okay? But this vertex, well, there's only one vertex altogether. So there's actually all of these vertices are all the same. So that means there must be one way when we go around and match up. At some point we have to go around and we come back down to the bottom when we're going around that vertex. Otherwise, if we just looped around here, there would be one vertex up in this top part, and there'd have to be another vertex in the bottom part. But we've already arranged that there's only one vertex. Otherwise, the two ends of the edge, say this end and this end, can't be identified. Which would be contrary to the result of step 2. All right, so suppose the common edge, the edge which is both in the top and the bottom is B, like this one here. What are we going to do? Well, we're going to cut. We're going to cut along here. So we're going to just cut along the top of the A's. There's a new edge. Let's call it C. And now we're going to take this piece here, and we're going to just glue it to the free edge B down here. So overlapping a little bit with my diagram, we're going to move it down there. And what does that result in? Well, that gives us now something. Well, there's an edge A there, and our edge C, and our edge A. And then there's some other stuff. And our edge C should be the same as in this direction here. Our edge C somewhere down here. Okay, now we're going to make another cut. Now we're going to cut along this edge. A new edge, let's call it D, and now there's that piece there. And where are we going to put that piece? We're going to put it, we're going to join the A part to the A part over here. So there's going to be the D part, and then there's going to be this other stuff. And that D is going, we haven't flipped it over, so it's like this. Okay? So we're moving this piece over there. And what does that result in? So we get, well, there's a C at the bottom, and then there's a D here, and then there's a C there, and then there's a D in this direction, and then this other stuff. And I realize now I probably, allow me to change the direction of D to make it a little bit more aesthetic. It doesn't matter, I'll just change the direction of both. Because that's the form that I want. I'll change direction, change direction. Okay, so I used to have two pairs of opposite direction edges, the A's and the B's, and they were separate. And now with these cuts and paste, I now still have two pairs of opposite directed edges, the C's and the D's, but now they're together. And they're together in a very particular form. If we read this thing, say, well, which way shall we read it? Okay, if I read it this way, for example, I would get C inverse, D inverse, C, D. Or I prefer to write it with the inverses at the back. So let's say E, F, E inverse, F inverse. Okay, so that's the normal form for pairs of opposite directed edges. And that's basically it. So now we just carry on doing that. If there's some more edges which are opposite directed, which are separate, then we just repeat the argument. These combinations, once they're together, they're never going to be separated. Because the cuts that we've made never go into the middle in some random thing. They're all related to the ones that we're using. So we just continue. Now continue until, well, all the same direction edges look like AA pairs, AA or BB or CC, and all the opposite directed edges have form A, B, A inverse, B inverse, or C, D, C inverse, D inverse. But that's not quite our theorem yet, because our theorem says that we can arrange so that we get either the sphere or only these ones. Right now we've got mixed. We've got some of these and some of these. So we need one more idea, a trick, very lovely trick. So this is our final step. Step 5 is to prove that a cross cap plus a handle is the same as 3 cross caps. All right, so let's illustrate this. So suppose we have an A and then an A. That's a cross cap. That's what we mean by cross cap, an AA pair. And a handle, we mean something like B, C, B inverse, or B in the opposite direction, C inverse. And then other stuff. Okay, so we're going to do some cut and paste to this. Okay, first we're going to cut along here. Let's introduce a new edge D, and we're going to take this quadrilateral, and we're going to move it out by adjoining it with the A side over there. And then that means this will have to be A followed by B, followed by C, and then going against the grain of D. Okay, so after we've made this cut and moved this over, we get D, C, B, then D, B, and C. Okay, now we make another cut. The cut we make now is from here to here. And let's call that E. And then we're going to move this piece over here, over on this side so that it joins the C edge there. And so we can write E, D, and that'll be C, and then E, and then D, and then the other stuff. So moving this part over here. And that gives us then E, another E, D, some more stuff, B, D, and B. Okay, good. And now we make one more cut. B, D, cut this along, say, F. And we're going to move this down here. Join the B edge to this B edge. All right, so that's B, and then coming in here would have to be F. And coming in here would be D. And then altogether that is say D, make it a hexagon. Hexagon. So D, E, E, D, F, and F. And one more cut from E to D. We're going to cut that part away. Let's call it that edge G. And we're going to glue it to the D part up here. That's just a translate. No, it's just a move it over. G, E, and E. And that's equal to F, F, D, E. So I move that part. That's equal to F, F, G, G, E, E. So F, F, G, G, E, E, and other stuff. And lo and behold, that is 3 cross caps. If we read it, say this way, we've got E, E, G inverse, F, F. 3 cross caps. So that means now that any mixture, of cross caps and handles can be converted to only pure cross caps. So whenever we have a cross cap together with a handle, the handle can be replaced by 2 cross caps. So a cross cap kind of eats a handle or converts it, mutates it to 2 other cross caps. So it can be converted to just cross caps. And so our list is just a sphere, or just cross caps. Things in form AA, BB, CC, up to DD, or just handles. Namely, things like form AB, A inverse, B inverse, CD, C inverse, D inverse, up to EF, EF inverse, E inverse, F inverse. Okay, that's sort of the proof of the classification theorem, and it's really a beautiful result. Well, I guess any one step is not too hard. You could perhaps imagine, if you thought about it for a couple of weeks, that you might be able to stumble across this proof. Although in fact, it took mathematicians many decades to figure it out. Now, there's one aspect of this that we need to finish to round off, and that's this issue of the Euler number that's going back to this fundamental number associated to things. So we have to connect this classification with the Euler number. Euler number of a combinatorial surface. All right, so the theorem that chi equals v minus e plus f is well defined on a combinatorial surface. So I have to just clarify, note that what does V mean? V means the number of different vertex types, not just the number of corners of all our polygons. Because if we just list all the polygons, there are many corners, but these corners come together on the surface to form vertices. And so the V really means the number of vertices in the sense we've been talking about, number of vertices or vertex types.
Classes?
Or equivalence classes, we call them, yes. And the proof is, in some sense, very simple, because the number of operations that we have from going from one combinatorial surface to their standard form is very simple. There are really only two operations. Okay? So the operations, well, the first operation was what? Well, we had some situation like where we had an edge A and another edge A. And that edge A, those two edges, A coming in, give a single vertex type A. Go all the way around, we go all the way around. So this must be some other type B. And when we collapse our pairs of edges, we get, let's call that, say, B and that's C, just to be specific. So that's B and C coming in, and our old edge A is now interior, and the rest is out there somewhere. So when we do this first type of operation, what happens to the vertices is that the vertices reduce by one. We're just losing that A vertex, which was all by itself. The edges, well, the edges are also reduced by one. We're losing the little A edge. The number of faces stays unchanged. And so the chi V minus E plus F stays unchanged. And our second operation, when we have something like this and we make a cut and then separate it into two pieces, say, the edge E. This basic kind of cut and paste business where we cut and separate or glue together. It's the opposite. Well, in this case, the number of faces goes up by one. The number of edges goes up by one because we're introducing this interior edge as a new edge. The number of vertices doesn't change. And so chi goes to chi. Doesn't change either. And now let's finally evaluating chi. If we have a number of cross caps, say A, B, B, C, C. Well, in this case, vertices will be 1, The number of edges is 3. The number of faces is 1. And so chi equals 1 minus 3 plus 1. That's 2 minus 3. Which in this case is minus 1. But in general, we can see exactly the same way that if you have k cross caps, then you're going to get 2 minus k. And for a surface which is just made of handles, let's do an example. A, B, A inverse, B inverse, C, D, C inverse, D inverse. Well, here the vertices is also 1. It's only one vertex type. It's in standard form. The number of edges is 4. A, B, C, and D. The number of faces is obviously 1. And so the Euler characteristic is 1 minus 4 plus 1, which is 2 minus 4, which is minus 2. And so in general, if we have n handles, then the Euler number is 2 minus 2g, or n, 2 minus 2n, n. In particular, if we know the orientability, then we know whether we're in this situation or in this situation. Then we can find the number of cross caps or the number of handles from the Euler number. Right? You just invert this formula or invert this formula depending on whether it's orientable or non-orientable. So the orientability type plus the Euler number determines the combinatorial surface completely. Determines the combinatorial surface completely. And that's a very important fact about compact two-dimensional surfaces. These, essentially the Euler number rules, plus orientability. So showing again how powerful and important the Euler number really is. Okay, you'll now want to play around, I know, building your own combinatorial surfaces. And you can do so now. You can just get polygons, label the edges in pairs, and build your own combinatorial surface, and you can figure out what it is. Okay. So let's do a problem or two. Problem 20. Apply the method of the theorem. To reduce to standard form. A, B, C, B, A, D, C, D. And problem 21, same for A, D, B, C, B, A, D, C. All right, so next time we're going to have a look at another more modern proof of this result due to John Conway. It's called the zip proof. And it It's similar, but it has a different flavor and allows us to think about the situation from another point of view. So I'll see you then.